Hello everyone, my name is Bindushra and today in this video we are going to discuss about the complexity of asynchronous prediction of majority automata. Abstract. We consider the asynchronous prediction problem for some automate as the one consisting in determining, given an initial configuration, if there exists a non-zero probability that some selected site changes its states when the network updated picking one site at a time uniformly at random. We show that for the majority automata, the asynchronous prediction problems is in NC in the two-dimensional lattice with neighborhood. Later we show that in 3 or more dimensions the problem is NP complete. Introduction. An automata network is a discrete dynamical system where a set of sites represented as the vertices of a graph G evolve over a finite set of states. The dynamic of each site is governed by a function that depends on the state of their adjacent sites. In this article, we will consider majority automata networks where there are two possible states and each site picks the state of most represented site between all its adjacent sites in the graph G. Formally, the majority automata is the one where the two states called active and inactive are represented by a set in the braces -1, 1. Coming to literature review, first point is synchronous prediction. In the synchronous setting, the prediction problem is relatively well understood, showed that the majority value can be predicted in log n rounds where n is the number of automata. This result was later improved to 0 of 1 rounds by 6. However, these results do not directly apply to the asynchronous setting. Coming to the asynchronous prediction, in the synchronous setting, the prediction problem becomes significantly more challenging. Showed that the asynchronous prediction problem is NP complete, even for a simple majority automata with two states. This result implies that there is no efficient algorithm for asynchronous prediction unless P equals to NP. Then coming to methodology, theoretical analysis, the first is model definition. Formalize the majority automata model, including the definition of the automata, the transition function and the prediction function. Second point is complexity measures. Define the complexity measures to be used such as time complexity, space complexity and communication complexity. Then the third point is lower bounds. Establish lower bounds on the complexity of asynchronous prediction using techniques such as reductions, diagonalizations, or information theoretic arguments. Then the fourth point of methodology is upper bounds. Develop algorithm for asynchronous prediction and analyze their complexity using techniques such as probabilistic analysis or combinatorial arguments. Then coming to experimental evaluation, simulation framework. Develop a simulation framework to evaluate the performance of asynchronous prediction algorithm on majority automata. And the second point is algorithm implementation. Implement various asynchronous prediction algorithms including proposed algorithm and baseline algorithms. Third point is experiment design. Design experiments to evaluate the performance of the algorithms under various scenarios, including different numbers of automata, states and prediction probabilities. Then the fourth point is performance metrics. Define performance metrics such as prediction, accuracy, convergence time and communication overhead. Then coming to results, the first point is computational complexity. The computational complexity of asynchronous prediction algorithms for majority automata is generally high due to the inherent complexity of problem. Then asymptotic convergence. Research has shown that some asynchronous prediction algorithms can achieve asymptotic convergence to the correct prediction, but the rate of convergence can vary greatly depending on specific algorithm and problem parameters. Then the lower bounds on the complexity of asynchronous prediction have been established, showing that certain algorithms cannot achieve better performance than certain threshold. Then approximation algorithms have been developed to achieve near optimal performance in practice, but these algorithms often rely on probabilistic methods. Then the final is conclusion. We had proven that in NC for majority rule in the two-dimensional lattice, which closes Moore's conjecture. This suggests that unless NC equals to P, a two-dimensional majority, CA cannot simulate montate circuits that are not planar, or at least a simulation that satisfies the robustness prosperity is not possible. However, the complexity of prediction and stability restricted to the majority rule and a two-dimensional lattice is open. The possibility that a monotone function in two dimensions and with a neighborhood is capable of simulating non-planar circuits seems unlikely. It is important to point out those results are not easily translated to other regular lattice with other neighborhood than 3 or 4 neighbors. For an example, two-dimensional regular lattice with 6 or 8 neighbors. We point out that in prediction is P complete restricted to the majority rule and graphs of degree 3. In contrast, in the same topology as is in NC. Thank you. Thanks for watching the video.